Ladies and gentlemen, welcome to video 26 in a series of video lectures which are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017 in Paris. Today we are December 11th in the year 2018, about a year later. Today we start investigating the solar surface, and in this first part of this investigation we will address the issue of cell sizes at the solar surface from observations. We are now back into a part of the Fivefold Sun as a book which deals with geometry, the two-dimensional solar surface, after an excursion into numbers and kinematic through the bounds of the solar cycle, its millennial oscillations. After we started in part 2 with the 3D constitution of the Sun, and now we are in 2 dimensions at the solar surface. The contents of video 26 today start with accepted notions, as usual in this series of video lectures. We will then go into the meta-analysis that was performed during the Fivefold Sun project and see what the results are. Accepted notions about solar surface cells are that the cells, for instance, the largest ones, the so-called giant cells, are magnetic in nature. Many surface cell categories, however, are convective in nature. It is not mutually exclusive. Some cells are postulated to be both convective in nature and magnetic in nature. There is also a variety of shapes that these cells can assume. Some are thought to be circular, some are thought to be polygonal. This entails some issues as to what is the correct parameter for the entire set of cell sizes to assess these measurements for their sizes. Then there is an important issue with the differential rotation. The larger the cell in latitude, the faster it is distorted by differential rotation, hence it is destroyed after some time. And the parameters, for example, the aspect ratio, will evolve over time. All of these issues and ambiguities make the assessment of the entire cascade, if any, of cell sizes at the solar surface an arduous task. Patrick McIntosh, who is the author of the canonical classification of sunspot groups, an American researcher, is one of the few authors who proposed such a full cascade of surface cell scales at the photospheric surface of the Sun, which is as shown in this table. You see we have on the top the giant cells, which were already introduced in part 2 of this work of the Fivefold Sun in one of our videos. Then there is what McIntosh called the intermediate cell, which is a sunspot group. Then we have supergranulation, very well known, mesogranulation, which is not accepted by all, granulation, which is the basis of this entire scale, and was first discovered by Janssen in the 19th century. But there may be other concepts for surface cells at the photospheric surface. Perhaps active regions can compete with sunspot groups. If sunspot groups are a cell scale, why not an active region? And if sunspots are cells or groups of sunspots are cells, why not a flux tube? So the hierarchy of cell sizes is not fully defined and is still partly open. In the same classification by McIntosh, 1992, he proposed characteristic dimensions for these linear dimensions for these cells. You see what they are, and if we use an average for this these two bounds, this is the hierarchy of cell sizes as of 1992, according to this authority, Patrick McIntosh. So now we go through the meta-analysis which was performed in 2017 in the Fivefold Sun project to arrive at a sort of an update of Patrick McIntosh's landmark classification. In the data, we will have two distinct categories of cell types, those that are fully accepted and those that are proposed and remain at least partly controversial. So the accepted types are the giant cells. We already investigated these in part 2, and now in this meta-analysis of 2017, supergranulation is looked into, 40 pages in this part 6 of the book, Granulation, 15 pages, flag tubes, short introduction. And for the more controversial cell types, we have also investigated the size of mesogranulation and the possibly lower scale mini granulation. But we kept the intermediate cell estimate of its size by McIntosh. For the giant cells, again, as found in part 2, there is a bimodal distribution. The cell size suggested originally by Bumba of about 400 megameters. 400 megameters is a horizontal diameter, and a larger peak in the distribution, a larger diameter at the second mode of the distribution, 45 degrees separation, which corresponds to 547 megameters. Then the intermediate cell, typical sunspot group according to McIntosh in 1992, 150 megameters. Supergranulation is often given as 30 megameters. We tried to refine this estimate, and after many methodological difficulties, for instance, the distinction between a horizontal diameter and a horizontal separation in the solar physics jargon, we arrive at about the same typical size, which is in our results 29.3 plus or minus 1.5 megameter, which is very close to the canonical accepted value of 30. You see, this is a table where the results found in the literature that could be used in the meta-analysis are put together, and we have a mean of 13 individual values, which is 29.3. We have a mean of 3 source medians, 29.5, etc., all very close to 29.5 megameters for supergranulation. As for mesogranulation, which is a controversial type of cell, not accepted by all authors, originally it was defined as a cell of about 7 megameter typical horizontal separation in 1981 by November. And more recently, from direct estimates, we have 3 other direct estimates. the average of which is found to be in our meta-analysis 7.4 megameter. Granulation is the best known, first discovered around 1900 by Janssen in Meudon. It is not circular. We should not use diameter. It is polygonal in nature. And the first approximations with modern instrumentations in the 1960s were about 2,000 kilometers, can now be refined around 1.7 or 1.8 megameter. We retain a typical value of 1.75 megameter, very close to Mackintosh's estimate in 1992. And then we go below the cell scales of 1992 retained by Mackintosh. And we learned that some authors, for example, Abramenko and collaborators in 2012, found that there is a typical concentration in the distribution of granules below a certain threshold. And they find a typical size for these mini granules, as they call them, less than 600 kilometers in horizontal separation. From their data is found in our meta-analysis that there might be two relevant characteristic sizes for these mini granules, perhaps 365 kilometers, perhaps 540 kilometers. So we put the characteristic value at a mean of these two bounds, which is about 450 kilometers. Finally, we can also propose, suggest to add at the bottom end of the distribution of solar cell types the flux tubes, which from a magnetic point of view would be the smallest conceivable cell size. And we look into what is the typical dimension of these flux tubes. And we find from these authors and collaborators recently in 2015 both their own results and a review of the literature that they themselves cited, that they the dimension of the flux tubes can be assessed from the bright points at which they seem to be located at the solar surface. And this might be from 140 kilometers to 220 kilometers as a diameter. So typical central value is retained at about 160 kilometers. So we can now put together these new estimates and try to update the numbers proposed by Mackintosh more than 2 decades ago. We see that the giant cell, now what is new is that we have a bimodal distribution, otherwise it is approximately in line with Mackintosh. We keep his estimate for this cell scale. Supergranulation, not much of a change. As for mesogranulation, it is reassessed at a higher value, but you saw in the previous pages that the value of 5 is not in the data, probably rounding by Patrick Mackintosh. And for granulation, also we propose that 1.75 is perhaps more realistic, better verified than the rounded value of 1.5. And then we have the new estimates for 2 scales below the granulation level, which was the smallest cell size envisioned by Mackintosh in 1992. Now we can try to see if there is a special kind of spacing between the characteristic cell sizes. First of all, we will find that the proposed or at least partly controversial cell sizes, as opposed to the accepted cell sizes, they are at alternate positions. You see, these are the accepted cells, and the controversial cells, which are not accepted by all authors in the literature, they are at alternate positions. The spacing between the sizes of accepted cell types seems to be of the order of 16 times or 11 times. You see, from giant cell to supergranulation divided by about 16, again from supergranulation to granulation divided by about 16, and here from granulation to flex tube only divided by 11. However, we are not very well informed on this value. And then again, the spacing between the sizes of the proposed or controversial cell types, they seem also to be spaced at a factor of 16 or perhaps 18 or 20. You see, from intermediate sunspot group to mesogranulation a factor 20, and from mesogranulation to minigranulation a factor 16. So if we now include both types in a continuous distribution, we have a mean of the factors between consecutive cell sizes of 3.9, which approaches, in fact, an integral value of 4. The discrepancies compared to the value of 4 are found here, where again perhaps we are not well enough informed on this value to be sure that this is below 3 or even below 4. And here, where instead of times 4 and times 4, we have times 3 and times 5, because this value is apart from the size which would yield to factor 4. Again, this is the only value that we did not revisit, and maybe it was, and it is very likely that it is a rounded value, which is in fact the least realistic in this entire set. So based on these set of values, we seem to have a rather realistic hypothesis that if there is any regular spacing in this distribution, it is ruled by a factor 4, and 4 times 4, i.e. 16. Now, if this is the case, why would cells, the surface of the Sun, be spaced at factors 4 and 4 times 4? If you reflect on the possible partition of the surface of a cube, which has 6 faces, hexahedron, 6 faces in Greek, just divide the edge of the face by a factor 2, and you find 4 cells in each face of the cube, so you get 24 cells for the cube. Is this feasible at the surface of a sphere? And what would be a procedure for a regular partition of a sphere as a surface, as a two-dimensional surface? And would this be an explanation for this cascade, apparent possible cascade of cell sizes ruled by a factor 4 and 4 times 4 at the solar surface? We are now finished with video 26 and the discussion of the observed sizes of cells at the photospheric surface. In the next video, we will introduce the possibility of an icosahedral cascade of cell sizes at the photospheric surface. I thank you for your attention.